This conference will now be recorded.
Guna madam, kindly mute yourself. Yes, okay. Thank you. So, Deepa, in the last class, we had started with alternating current. Okay, we know alternating current will change its magnitude and direction periodically, and we have learned that alternating current can be expressed in terms of sine function or cosine function, which I can say sinusoidal function like this. If I write current I is equal to I0 sine omega t, I can write like this, or EMF I can write E0 sine omega t. If there is some phase angle between these two, then I can write this. Okay, so this is what we have learned, that any quantity which is alternating quantity, basically here we are learning AC current or voltage, or AC current and EMF. So these two quantities can be expressed in terms of sine function, okay, or cosine function. So sine or cosine, actually they both are called sinusoidal function. Sinusoidal function. When I say sinusoidal function, then I can either use cos omega t or I can use sin omega t. So these both together called sinusoidal function. Anyway, so today's topic is what is phasor diagram, and if we apply AC signal to a pure resistor or purely resistive circuit, how current and voltage are related to each other in terms of phase, and how their magnitude varies, etc. in AC. We have learned these things like Ohm's law in case of DC, but we'll see whether it is applicable for a resistive circuit in case of AC signal also. So these are the things we'll be learning today. So let us start with phasor diagram. The first topic is phasor diagram. So before I say what is phasor diagram, let me tell you what is phasor. Actually, phasor is a rotating vector. Phasor is a rotating vector, and this rotating vector can represent or produce a sinusoidally varying quantity, whether it is current, voltage, or whatever it is. If any quantity, suppose A, which has some instantaneous value, and this value, instantaneous value of that quantity, if that is varying with time as a sine function, okay, or as cosine function also I can write. So if this is varying sinusoidally, then rotating vector can represent or produce this sinusoidally varying quantity A. Okay, so that rotating vector is actually called phasor. So as a definition, we can say a rotating vector which represents sinusoidally varying quantity is called a phasor. Okay, we'll try to understand diagrammatically. See, I have a schematic diagram over here, and I said phasor is a rotating vector. See, look here, there is a rotating vector. Suppose if I say this is O, the origin, and this is A. So if suppose I have a vector OA, and this rotating vector generally what it does, it rotates. See, suppose it was here at 0 angle sometime, it rotates actually in a circular path. Rotating vector rotates in a circular path. That means from all the way, if I say theta is the angle between this suppose x-axis, this way x-axis, this is x prime, this is y prime, y prime here. Then the rotating vector will rotate in the anti-clockwise direction in a circular path. So all the way from 0 to 360 degree it rotates. Okay, rotating vector rotates in a circular path from 0 to all the way up to 360 degree. See, like here 0 degree the position is here. Then when it is at 30 degree the position is here. 60 degree position is here. Then 90 degree position is here. This is 270 degree. This is 180 degree, and here again 0 or 360 degree at the same position. So this is how when a rotating vector rotates anti-clockwise direction, then it, see, the magnitude and the projection of this rotating vector will represent the instantaneous, respectively the amplitude and the instantaneous value of the quantity. Here suppose I take current which is varying as this. So I is equal to, so I is the instantaneous value, and this is Im sine omega t plus phi. Okay, phi is the phase angle. Together with this, omega t plus phi is the phase angle. This is actually phase angle. Phase angle. Okay, and this is amplitude. It is very important to know which quantity is called what in AC signal or any wave equation. This is actually instantaneous value. Instantaneous value of current. Instantaneous value means at each instant of time. Suppose at 1 second, then 2 second, 3 second. What is the value? You just put the t over here. See it. If you put the value, then you will get it. Okay. You'll get the instantaneous value. All right. So this is the mathematical part. But what this how this rotating vector or a phasor can represent or produce this whole sinusoidal signal? Look here carefully. Generally, rotating vector will rotate with an angular velocity. Okay, with an angular velocity equal to the angular frequency of the quantity which we wish to represent with the phasor diagram, or we wish to represent the signal by rotating vector method. So what it says, rotating vector rotates with an same angular velocity as the angular frequency of the quantity. Suppose in this case the angular frequency is omega. So the rotating vector rotates from 0 to 90 to 180 to 270 degree. Again come back to here. 0 degree with an angular velocity omega. With the same velocity, it will rotate, but it will rotate in the anti-clockwise direction all the way from 0. And look, the length of this vector will give you the amplitude, that is Im, and see, instantaneous value of this quantity will be obtained from the projection on the vertical axis. If I have vertical axis, this one, look, I'll take the projection here, vertical axis, look here, this one at 30 degree. This is the value at 30 degree. If I say 90 degree, this is the maximum value over here. So this is the value. At 0 degree, this is the value. So I can easily connect these points and I can draw the curve. Okay. Similarly, 150 degree is here. Okay. 180 degree again 0. 360 degree again 0, but that 0 position is not the same. Here 360 degree, here 180 degree. Okay. Again 270 degree, it has sine curve has minus maximum value minus 1. Okay, so this will be minus m, im, minus im. So this is how, see, at each instant you can find out. See here no vector position is there, but if I have something, I can get this here also, like that. If you take the projection on the vertical axis, this will give you the instantaneous value of the quantity here, current. So this is how a phasor or phasor diagram helps us to represent any sinusoidally varying quantity with a proper phase. And we can see in alternating current here, we will be representing the current and the EMF by phasor diagram, and with this phasor diagram we can easily represent these two quantities, EMF and alternating current, just by two vectors in the phasor diagram along with proper phase angle. And by just seeing the phasor diagram itself, we can get clear idea about their values, what is the relation between them in terms of phase, which one is lagging, which one is leading, etc. You might be thinking I am talking so much, but no, I am just going to show you something here, this phasor diagram, just to make your understanding more concrete. I'll just show you this phasor diagram here. Look, the phasor diagram represents alternating current or voltage in our chapter, this chapter mainly, but it can, phasor diagram can be obtained for any sinusoidally varying quantities. But here specifically for our purpose here will be representing current and EMF or voltage, alternating current and voltage in terms of phasor diagram. So what phasor diagram gives, it actually represents alternating current and voltage which has the same frequency, okay, as two vectors. So these two vectors, they are rotating anti-clockwise direction from all the way x towards y, and y to again x prime to y prime, and then this. Okay, this is rotating with angular frequency omega, because angular velocity omega, because the angular velocity of the rotating vector has to be the same as you have the frequency, angular frequency for these two quantities here. Okay, the same angular frequency is there for these two quantities. Okay, first of all, these two quantities, alternating current and voltage, they are having the same frequency. Okay, and another point is the rotating vector, they are rotating anti-clockwise direction with the same angular velocity, as the signals or alternating quantities. So if these two quantities I and E, they are not having same frequency, then we cannot represent in a single Phasor diagram. Okay, in that case we cannot represent current and voltage in same Phasor diagram. Okay, so that's why when we draw Phasor diagram for two quantities, those two quantity must have the same angular frequency. Here it is omega, and my phase. So rotating vector here, two rotating vectors I have taken for two quantities. One is for EMF E, which is OP, and for current here we have taken OQ rotating vector. Look here, the length OQ or OP, the length of OP will give you the amplitude of, here OP is amplitude of this is EMF, which is what? Which is E0 here, and length of OQ, this will give you amplitude of current, which is I0. So which is denoted here, look this thing. So this vector is actually representing your EMF. So it has magnitude E0. So the length of OP will give you the amplitude, which is E0. Now you take the projection at any instant. Suppose this is at t second. Okay, at t second both the phasors have these positions. One is C. So OP is having actually phase omega t. Phase means the angle it makes with the x-axis here. This is origin, this is x-axis. So the vector OP is making an angle omega t with respect to x or with x axis. So the angle, look, POX, this is omega t. This angle is omega t. And this is the phase angle for the EMF. I'll just remove this part. And the angle QOX, this angle is the phase for the vector here current OQ vector. So here this is the current. So what is the phase angle for that? What is the phase for the current? This is the phase for the current, omega t plus phi. Okay, omega t plus phi. Now look at this particular position. If I take the projection on the vertical axis y, OY, here look this position, the projection is this one, this is I, this is actually giving the instantaneous value. Instantaneous value means this one, okay, which I can write I0 sine omega t plus of phi. Okay, and E also I can write E is equal to E, this is the instantaneous value, E0 sine omega t. Okay, this is, so EMF has phase omega t, whereas the current has omega t plus phi. So in this case we can say that the current is ahead, okay, it is ahead by phase angle phi. Current is ahead by phase angle phi, by phi. Or in other words I can say EMF is lagging behind the current by an angle of phase phi. So this is how I can write. Okay, so look here, I'll clean everything. Look, this vertical projection of this OP vector on the vertical axis OY give will give you the instantaneous value of the corresponding quantity. Like your projection of OP vector gives the EMF, and projection of OQ vector on the vertical axis gives you the instantaneous current. And look, they are actually rotating, both the vectors are rotating in the anti-clockwise direction with the frequency omega. Okay, oh sorry, angular velocity omega. So this is how Phasor diagram. See, the important thing you look. Okay, I think I have done some mistake over here. This will be only this part. Okay, because it has only sine omega t phi. So current has omega t plus phi phase. So here it is this much alone. Okay, sine omega t. So E will be E0 sine omega t. In the figure it is a mistake while typing. So this is the Phasor diagram. So mainly what we are seeing here in alternating current, this chapter will be representing alternating current and alternating voltage or EMF by Phasor diagram, just to simplify and see the relation between voltage and current, what is the phase angle between them, which one is ahead and which one is lagging behind, and by how much angle. So these are the things which we will be representing, and rotating vector method is very important and very easy to represent any sinusoidally varying quantity by this Phasor diagram. And from just by seeing the Phasor diagram without any calculation, you can get all the information just by seeing this diagram. That's all. This diagram will give you all the information. Like see here, current has uh, amplitude I0. Okay, and if you know the length of this vector, then you will get exactly what is the amplitude. The projection, if you know exactly the value, then you get the instantaneous value at particular instant of time, and you know what is the phase at that particular point. Okay, if I say OQ vector, it has phase omega t plus phi. Okay, and things like that we can understand. And if you draw two vectors, we can compare the phase between them. How are they related with each other by phase? Which one is lagging? Which one is ahead? Kind of those things we will be learning. Okay, so it is very useful method just to avoid rigorous mathematical calculations. Okay, now we will be applying AC signal to a pure resistive circuit or pure resistor in a circuit, and then we will see things like what is the current in the resistive circuit, what is the current if I apply certain voltage, what is the current, what is the power dissipation, what is the average power dissipation. Okay, and then how do we relate these results with our DC case. Okay, now let us see. Then we are just having AC signal, we are just sending AC signal in this circuit where I have only a resistor and there is nothing else in the circuit. So this kind of circuit is called actually purely resistive circuit or pure resistor circuit, resistive circuit. Okay, so here the EMF is E and the resistance is this. So suppose this battery is giving EMF to the circuit which is varying sinusoidally like this, is equal to this. I'll write as a time function of time. This is instantaneous value of the EMF which is sent by this AC generator to this resistor to sine omega t. Now if I say the current is I, then what is the voltage drop in this circuit? There is nothing, no source of voltage drop. So the voltage drop will be I into R in this case. So this current I am taking as IC current because my signal is AC signal, or the EMF across the resistor is AC. So the current also will be the AC current or alternating current. So now if I write Kirchhoff's law for this particular circuit, what I get is actually E is equal to IR. This is the KVL. Applying KVL, excuse me. Applying KVL, we can get this thing. Okay, now what we'll do, I'll write the value of this one, EMF. The value of the EMF or the expression of the EMF is E0 sine of omega t, which is equal to I into R. So if I simplify a bit to find out the current, this is E0 by R sine of omega t. So you can see that this is the current expression for the current. So this side also will be having at least this E0 by R has the dimension of current, and that is the maximum value or amplitude of the current in this circuit. So I can write this value as I0, or in your book it is written as Im. I'll write as I0 sine omega t, where I0 is actually E0 by R. This is the maximum current. I0 is the maximum current in the circuit. So this is called amplitude of the current here. Amplitude. Okay. So what we have done here, I'll repeat it. I have a resistor. I have made a circuit where I have only a resistor and AC generator or a battery which can produce AC signal or send AC signal to this resistor. Okay. Now after closing the switch or making that closed circuit, you will see there will be EMF across this resistor R, which is alternating or alternately becoming positive and negative, like positive here or negative here. Also it can be negative and positive, so it can vary sinusoidally, as you know. It will change its sign. So if I apply such a voltage, such an AC voltage or alternating voltage or EMF, what will be the current in the circuit? So for knowing that, we have already learned that Kirchhoff's law will help us to find out current for any complex loop. So this is not a complex loop. This is a very simple loop or simple mesh of the circuit. So we can easily write the KVL for this circuit. So where it is E is equal to I into R, where I is the current. I am just considering that the current in the circuit will be I. So I can write this as EMF is equal to I into R. Okay. Now what I have done, I have just put the value of E. So the value of E is actually, or expression of E is equal to E0 sine of omega t. If I write that, and then I can find out I. So what I get, I is equal to instantaneous current I is equal to this I0 sine of omega t. I'll just erase this down part. Okay, so see, I have written two equations. This is equation 1, this is equation 2. So you can see that this is current, this is alternating voltage or EMF, and both are function of sine. So both are function of sine omega t. That means what? If both have sine omega t, so you can see these two are having same angular frequency. They have the same phase angle. So both are having phase angle omega t. That means what I can say? In a pure resistive circuit, if we apply AC signal, the current what will be flowing in the circuit is in the phase of this battery, okay, or the EMF. So you have same phase for current and voltage over here. And what else we can get from here? You look here, this I0 we have written as E0 by R. That means your I0 will be obviously less than E0. So this is actually amplitude of the current. So amplitude of voltage divided by R. So this gives the amplitude of the current. So if we so when they are in phase, voltage and current are in phase, you know what happens? Both current and voltage will be having their maxima, all maximas and minimas at the same point. You look this curve, this is actually Vm. It shows here Vm. I'll write V0 because we have written, okay, V0 instead of V0 we'll write E0. E0 EMF here. This is the E0. This is the I0. Okay. So you can see that both are same phase, means their maximas and minimas are at the same position. See, for both the curve, this is the minimum position. This is the -1 here, minus V0 I can say. Here I can say minus I0, like this. And these are 0, see 0, 180 and 360. These points are having 0 values for both the signals. Okay, that is E0 sine omega t and I is equal to I0 sine omega t. Okay, so these are actually the expression for the current and voltage in case of AC. Uh, in case of pure resistive circuit. Okay, now we'll see the phasor diagram for this. How we can represent this current and voltage for purely resistive circuit in a phasor diagram. So we know what we have to draw in phasor diagram. I have to draw two vectors with proper phase angle. Look here. Okay, maybe I'll just magnify this portion I have taken from ncert textbook itself. I'll magnify here. So in this case, since both are having same phase sine omega t, okay, sine omega t, look, I'll write the expression what we had. E is equal to E0 sine omega t and I is equal to I0 sine omega t. Okay, so both are having same phase. So if I draw a rotating vector for current or voltage, they will be actually lying on each other, lying on each other. Look, if I say this is, see, as I said, this amplitude of this current is less than the amplitude of the voltage. So I can take a vector like this. Suppose this is O, this is A. So OA vector will give the represents the voltage and current together. But see, this is up to here. Up to here, this will give you the current. Okay, this is the amplitude of the current up to this portion, and up to here, this is the amplitude of. So the whole length will give you. So whole length of OA will give you amplitude this. If I say this is P, so OP, length of the OP will give you this I0. And since they have the same phase angle, omega t here, omega t here, same phase angle, that's why they are both coinciding on each other. Okay, coinciding on each other. Now look, if I just take the projection vertical axis, on the vertical axis, this is the projection. So this will give you the instantaneous current IT, and this projection you look, this will be actually E of t. Okay, E of t, instantaneous value of the EMF. So this is what is represented in this figure. You look here. So here they have written, instead of writing omega t directly, they have written omega t1. See, this is the gray color. Up to gray color, this is the current, and up to this is voltage V. They have written voltage of the signal is V0 sine omega t. That's why the drawing is, in the drawing it is written V, and both are actually rotating in the anti-clockwise direction. And the vertical projection, look, this one gives the current like this. You have to write I0 sine omega t1 here, I am sine omega t1, and projection for the voltage is this one, which gives V0 sine omega t1. Okay, so this is the phasor diagram representation of both current and voltage. You look in the other side, this curve B, look B. So I can just generate the curve. See, for current, I can generate the curve. See, first this point, at this particular point, this, if I draw this here, the value one value, and at 0 another value we get. So I can easily draw the curve. And similarly, the voltage curve also I can draw just by extending the projection on the other side. Okay, I can just draw it. That means what I'm trying to say, if you have, as I have shown in the previous case, so if I have pulse vector here, so you take vertical projection over here. So this is the value, suppose. At 0, this is another value. You take here, so up to here, this has another value, suppose here. At this 90 degree, it has the highest value, maybe here. So you can easily draw the curve like this for all the position of this rotating vector. Okay, just by taking the vertical projection. And in some cases, like see 180 degree, 0 degree, and 360 degree, there uh, value will be same. Okay, that is 0, since it is sinusoidal expression. Okay, I think you have understood how. Look, if you are asked to draw the phasor diagram for current and voltage when an AC signal is applied to a purely resistive circuit, then in the exam you have to draw in this way. Okay, give some name O to A. This will give you the EMF, and you have to draw actually on the same line another vector which is lesser value than OA. Suppose this is OP. So this part will give you the current. This part will give you the voltage. So projection of this part. Okay. So this is how you have to draw. Obviously, you have to specify the angle and rotation. You have to give the direction rotation like this. This is omega t. This is how you have to draw Phasor diagram. And just by seeing the Phasor diagram, we can get many information about the quantities. Now we'll just go to the next part of it. So we have seen that AC signal, either voltage or current, can be represented in this case, especially what we have seen that E is E0 sine omega t, and I is I0 by R, or sorry, E0 by R, or this I can write as I0 sine omega t. So both are actually sine function, and see, we know that sine curve varies like this, and my drawing is not very symmetric, but it is a symmetric curve. That means if you have here, if I say the current, so this side is positive I0 and this side will be giving you a negative I0. Then if you take an average for a full period or full cycle, so you will get actually U minus of I0 by 2. So this will give you the average of the current, alternating current. If you just simply take the average, so this will be 0. So that's why we had discussed in the introductory class also that we cannot simply take a full scale average. Okay, we have to take average in half cycle. We cannot take full cycle average of this kind of curve, sinusoidal or sine or cosine curve, or otherwise I can just square it up and then take the average, which will be non-zero. So now what we'll be seeing that the average current or average voltage in resistive circuit can be 0, as I have told you.
Not clearly your voice.
Hello, hello. Okay, Deepa, there was some disturbance from your side. Anyway, now it is all right. So we have seen that if I take average full cycle, it will be 0. Similarly, if I take average full cycle for current, this also will be 0. But does it mean that the average power dissipation through the circuit also will be 0? No, it is not 0. Average power dissipation will not be 0, even though the average current or average voltage will be 0, but average power dissipation in the circuit will not be 0. There will be joule heating. We know the power. So if I write instantaneous power, then I can write instantaneous EMF here E, or I can write this as EMF as, and I can just simply write this as this thing. Okay, or I write this into, so we know P is equal to V into I. So here my I is IT here, V is E of T. Okay, so I'll write the expression for both of them, E0, and here it is I0. I'll write this in, and then you get sine square omega t, because both are having sine omega t, so sine square omega t. Okay, or in other words I can write average power joule heat, sorry, this is power Joule heat loss will be actually I square R. Okay, I square into R. That means you get I square, I naught square sine square omega t into R. If I write, this will be sine square omega t. Now, if I take the average of this power, this is called actually instantaneous power. I'll write it for your sake. This is instantaneous power. Power in the circuit. Instantaneous power. So if I take that average of instantaneous power, then look what I have to take. Average for I square R. That means you have your I0 square R sine square omega t whole square. Okay. Sorry, this is already there. Also, it will be average of this. Now look, you have these two are constant, independent of time. I0 and R, they are independent of time. Independent of time. So I can take them out of this average, and only thing is that we have to take the average of sine square omega t. You might be thinking, sir, why sine square omega t doesn't go to 0 if I take average in full cycle? So what we have now, average power means average power dissipation. This is average power dissipation. So I have I square R, so which is I0 square I into average of sine square omega t. So this average means, in terms of integration, we can write like this. Okay, any quantity, if I have to get average, I can write this. Say I can write this average sine square omega t as, just by following this one, we can write 1 by t, 0 to t, f of t means here sine square omega t into dt. This is how I have to write. So what is this capital T? This is the period, time period, okay? Time period. This is a time period. Now you have to integrate over this thing. So you can do one thing. You can just multiply. Uh, so you can write 2t. So you will write over here. You can just, so 2 sine square omega t into dt, and this you can write as 1 plus sine omega t, cos 2 omega t. So what you can write here is 2t here. So integration 0 to t 1 plus cos of 2 omega t. Okay. So if you integrate this, okay, if you integrate this, so I'm not doing the whole integration over here. If you integrate this, what you get is actually, so average power, average instantaneous power will be I0 square R, and here sine square, average of sine square omega t. From here you will get actually half. You get I0 square R by 2. Okay, this will give you, if you just write in this fashion, do integration 0 to t, then you will get half for this. Okay, Or is the sound not very clear? What is the situation now? Is the sound clear now? Guna madam, how are you hearing? Is my sound clear now?
I can hear Ram. What about
Oh,
Deepa?
I don't know. Then maybe this is the problem. Deepa, are you able
Deepa?
to hear me properly? Maybe this is the problem with her internet.
Okay, okay. What about you? Deepa? Answer, ma.
Is it audible to you clearly? You can write in the chat box. Okay, I'll continue. If you have some problem, you write in the chat box. So you can see the average power. What we get here is this I0 into R by I0 square R by 2. This is in case of AC. But what we know, average power or joule heat loss in case of DC circuit, we know I0 square into R. Actually, in DC there is no instantaneous value. Actually, the instantaneous value and the amplitude is same in that case. So you get I square R. But here we are getting half of this. Just to keep the similarity in these two cases, this is AC, this is DC part. So just to keep the similarity in the expression of this joule heat loss or power dissipation, average power dissipation, we had to define a special amount of current. Okay, special amount of current which is equivalent to DC current. Okay, so we'll define a special amount of current which is called actually RMS value. Special is that RMS value of the current which is equivalent to the DC current, which can produce the same power dissipation as DC. So what does this mean? RMS current, actually RMS current, IRMS, is such that it will produce a power dissipation same as my DC gives. So this is a special amount of current or special quantity. Okay, this is the current, but this is a special amount of current, RMS square root mean square value of current, which is equivalent to a DC current or ever. So it is equivalent to a DC current in terms of the power dissipation. That means this RMS value is the current which can produce power dissipation in the purely resistive circuit as I square R. Because here if I just take the instantaneous value or normal value of the current, I get half of the power dissipation of DC as our average power in AC circuit. I'll just clean it and then I'll write clearly. See, we have seen here average power in AC in case of purely resistive circuit, what we are getting as I0 square R by 2. But in case of DC, we know for the same current, we will be writing just I0 square R if this I0 is an average value of current. Okay. Just to keep the similar expression, we'll be defining a current, that is RMS current, root mean square, which is actually denoted by root mean square. That means mean square, root mean. And okay, so I'll just come from here. IRMS means you just come from back. Okay, come from back, square a quantity, square a quantity, then take the mean. Okay, take the mean and then root. So I have I here. So IRMS means I have to take square of I0. That means the amplitude of the current. Just take the square of that and take mean of that. Mean means average, and then you get the value, get the square root of that. You will be giving you this RMS value of the current. So I will be getting a relationship between I0 and RMS value. RMS value I will be denoting simply as, if I just denote simply as I, like this, or maybe I'll just denote as small I. I'll denote as small I RMS value of the current. Then look, I have a relationship between I0 and this RMS current, that is, so this is actually uh, no, this has to be actually I0 square by 2. It has to be I0 square by 2. Okay, so that then it will be I is equal to I0 by root 2. So average value, this is average. Okay, the average value or amplitude of your current will be always root 2 into IRMS. Here if I write suffix RMS. Okay, this is the relationship. Okay, so the amplitude or the average value of your AC signal will be twice root 2 into IRMS. So this is the relation. Now I'll just tell you. So I have got IRMS is equal to I0 by root 2. Okay, I0 by root 2. So now if I write power, average power, as with the RMS current, IRMS square into R, look what we will get is, we already will be actually, see, we know average power as I0 square R by 2. So if you just replace this I0, I'm sorry, just a minute. So this is the average power we know. Now we'll be replacing I0 square in terms of RMS. So if I write this as RMS means RMS is square, then this is 2 into IRMS into R, and obviously there will be a square over here. This is the relationship between RMS value and the amplitude. So if I just replace this amplitude I0 with RMS value of the current, then we'll be getting, see, this will be getting as IRMS square into R. Okay, so this is actually equivalent expression for the DC. So now AC has equivalent expression for the average power as DC. Both actually has expression I square R. Okay. Earlier what we got, average power, AC average power, this I0 square R by 2. If I just simply write the amplitude, but now I have defined a special amount of current which is equivalent to an average current or DC current, which will produce the average power dissipation in the circuit same as DC. So it is, that's why this is called effective current. IRMS is called an effective current. IRMS is called an effective current which can produce power dissipation same as DC, same as DC power. Okay, same as DC circuit. Okay, so this is how we can learn what is RMS current or RMS. So defining RMS quantity for any sinusoidally varying or alternating quantities, whether it is voltage or whether it is current. So if I just write this for voltage also, you will get, see, if I write voltage for VRMS also, you will get V0 by root 2. V0 by root 2. So I get IRMS, small IRMS, RMS is equal to I0 by root 2. Okay. Now if I write this V is equal to I, then I'll get, sorry, so we'll get V0 I0 by 2. Okay. So this I can write again, V0 by root 2 into I0 by root 2. Okay, so this will be actually RMS quantity. So this is actually the average power. So this is how we can write as power. So in this case we have what we have seen in AC case also, V is equal to IR. This is valid. This is Ohm's law. Okay. In AC case also, we can see in case of purely resistive circuit, V is equal to IR. Ohm's law is valid. Okay, V is equal to IR. This is valid for Ohm's law. But in this case, this quantity is actually RMS quantity. This is RMS value. Okay, and this is also RMS value. RMS value. So it is actually valid with RMS value. You'll get the similar expression or equivalent expression for equivalent expression with DC if you use RMS quantities of this, both voltage and current. Okay. So here in this graph, see, Im is actually the amplitude here in this curve, and capital I is the RMS current. So in this graph, it is represented like what is the value, like how they are related. It is represented. You can see this RMS value is an average quantity, an average or DC equivalent current, average quantity, RMS. So that's why you look here. This is not varying with time. This is the one written as capital I. So this is actually DC equivalent current or average current or effective current which can produce power dissipation in the purely resistive circuit same as DC. And see, I have shown you the relation between I and the average value I am here is this. This is the amplitude and this is the RMS value of the current, and this is nearly 0.707 of IM. That means RMS value of the current will be nearly 70 percentage of your I0. That means your amplitude. Okay. So this is the 70 percentage of the maximum value of the current or amplitude of the current. So your instantaneous value, okay, instantaneous value is always greater than your RMS value. So that's why whenever we say 220 volt, okay, 220 volt, then if you want to find out what is the effective current, you have to just multiply root 2 along with this. So this is the RMS value. This is actually RMS value, but not the actual amplitude. Okay, if you want to get the amplitude, you have to multiply with this, so you will get almost 311 volt. 220 volt means 311 volt. That is the maximum value of this particular voltage. It can vary within plus or minus this 311 volt, okay, or 311 voltage, plus or minus 311 voltage. Okay, so with this we'll stop it here. We'll meet again on Wednesday with the next part of this chapter. And thank you for your patience, Deepa. You have any question, query? You can ask me. I did not get you properly. Is there any problem? Any doubt? Okay, if you don't have any doubt, then I'll stop it here. Okay, so see you on Wednesday. Bye for today.